Hi, everyone. We've set up this Being an Engineer podcast as an industry knowledge repository, if you will. We hope it'll be a tool where engineers can learn about and connect with other companies, technologies, people, resources, and opportunities. So make some connections and enjoy the show.
What is it that we're trying to do? Our business, right? What are we trying to, for the customers we're trying to serve, how can we best serve them?
Hello and welcome to another exciting episode of the Being an Engineer podcast. Our guest today is Idara Uko, who holds bachelor's and master's degrees in electrical engineering, as well as an MBA. Idara currently works at Medtronic, where he serves as Director of Software Operations. He has over 15 years of experience in the regulated medical device industry, including R&D, market assessment, market development, understanding voice of the customer, system design, system verification and validation, and product support. Idara, thank you so much for being with me on the show today.
Hey, thanks, Aaron. Glad to be here. It's exciting.
All right.
Yeah.
Well, what made you decide to become an engineer?
To become an engineer, wow. Okay. Really, that was kind of easy for me. It started way back from when I was a kid, but my dad was a mechanical engineer.
But then you chose the dark side of it, electrical engineering.
Yes, I sure did. I'm like, I didn't want anything mechanical, but no. So I went into electrical engineering. My dad, and then I had a cousin that I looked up to who grew up with me. He was about 6 years older than I was, and he was interested in engineering. So all tried to be like him too. I chose the engineering path, but yeah, I had a lot of influences in my life that caused me to choose the engineering path. So, yeah.
Excellent. Yeah. All right. I'm going to ask a question that's just going to expose my own ignorance here, but you graduated from McMaster University, and
Yes.
At least those of us in the mechanical world are very, very familiar with McMaster car. Is there any relation there, or are they totally nothing to do with each other?
No relation at all. So McMaster University is in Canada, Hamilton, Ontario. And it's actually after a famous person in Canada.
Got it.
So,
okay.
Yeah.
Now we know. All right.
Yeah.
Can put that one to bed for good. All right. I'm going to continue asking questions that totally expose my ignorance. I am not, as some of the people I work with say, I am not sparky. I'm not very good with electrical. So I'm going to ask some really basic questions under the assumption that there are others out there like me who may be whizzes in mechanical engineering or different kinds of engineering, but don't have a firm grasp on electrical. So my first question here is, what is the difference between firmware and software?
That's a good one. Yeah. So firmware is okay. Let me back up a little bit. I studied electrical engineering. As part of your normal studies, you get exposed to computer engineering and software design, and with that, I gradually, as I went into work for the first time, right after my internship and graduated, I got a job as a firmware engineer, and I was doing more firmware tests. And at the time too, it was new for me learning this, but firmware, you think of firmware as embedded software. So it's software that runs inside of a device, right? And then you can think of your regular software as something that, you're working on your software application, something that faces a customer, that you could consider software. So you think of the cloud or your software applications. But firmware is quite neat because it's really the internal logic of a device and how it runs, and it still follows very similar principles as regular software, but yeah, we call it differently. So firmware is essentially embedded software.
Would it be accurate to say that firmware does not have a GUI, but software does have a GUI?
Correct. That would be accurate.
Okay.
Yes. Yeah.
Excellent.
Yeah.
I always kind of had a sense firmware is like it's in the PCB doing its thing, but I think that was a good distinction for me right there. Firmware, there's no GUI associated with it.
Yeah, excellent. See, you're more than Sparky already.
Maybe a tiny little glowing ember somewhere in there.
Good.
All right. You have spent quite a bit of time working on next generation implantable pacemakers and defibrillators. And this is all in your LinkedIn profile. And of course, without disclosing anything confidential, can you share a little bit about how generally these devices work, implantable pacemakers and defibrillators?
Okay. Yeah. Like one of the things that for me when I first joined, the company was I was out in California walking around at a conference, and I came across Medtronic, and they were they were recruiting and interviewing, and I saw a post there that said, "Hey, we're looking for electrical engineers," and I'm like, wow, you can actually. I can use my electrical engineering degree because then initially my direction was wireless communications. So I said, hey, you could use my electrical engineering degree to actually help people. And that's the way I saw it, right? So you had a company that is actually focused on helping people live better lives, right? So, and I'm like, you can actually, it's all based on electrical engineering type principles. Right. So the heart all works. Your body essentially has electrical signals that run through it already. Right. So based on those type of principles, we're able to come up with different devices. So a pacemaker, an implantable pacemaker is something that goes inside your body, under your chest, just around to the right or to the left, but below your breast. And it's somewhat what it does as a pacemaker essentially paces your heart. So you find patients who have, they have syncope, or they have cases where the heart does not beat as regularly as you would expect. So it could sometimes skip a beat, it beats really slow. So you tend to find patients who are, you could have patients who are weak and lethargic, and it's made just because their heart's not beating as fast. So if you're not beating at a regular rhythm, you're not pumping blood properly through your body at a regular rhythm. So what a pacemaker does is when the heart's beating too slow, it regulates the heartbeat. So it brings it back up to a normal heartbeat. And it does this by simply sending small electrical pulses to the heart, and then the heart is able to contract, right? So it contracts with each electrical pulse, and that enables the blood to pump, for the heart to pump blood across around the body. So that's what a pacemaker is.
Are they more commonly used to speed up a heartbeat or to slow down heartbeats or all of the above?
It's more commonly for pacemakers. It's more commonly to speed up the heartbeat. It's usually for patients where their heartbeats are too slow. So on average, your heartbeat's at about 60 beats per minute, right? So in some cases, some athletes, it's a lot faster naturally, but then you can get to, or it could be slower too for some folks. But in cases where you have some heart problems, you can have patients that are heartbeats of like 30 beats per minute, right? So that's way too slow, and that's where the folks get lethargic and other things. And so what the pacemaker does is it brings that back up to 60, right? And the interesting thing about the pacemaker is it also needs to be smart enough to say, hey, this person is exercising, so I need to beat a lot faster. So if you're exercising, you're getting up to 100 beats per minute. So the pacemaker needs to be able to say, all right, I need to adjust and help this patient continue to exercise without feeling tired. So it speeds up its electrical pulses so it can catch up. So
that is interesting. I had never even considered the intelligence to regulate the heartbeat depending on levels of activity.
Yep. Yep. And
How
another tidbit there is when you sleep, your heart rate also drops, right? So when you sleep, your heart rate drops to what, 40, 50 maybe beats per minute. And the pacemaker has to be smart enough to know that, hey, my patient's asleep, so I need to dial it back a little bit, right? And not keep it too
interesting.
high. So it picks that up.
Now, I would think that in order to regulate the frequency with which it stimulates the heart to beat, it would use, a heartbeat as the input, but of course the heartbeat is the output. So again, as long as you're not giving anything confidential away, how does the intelligence work to know, if you're playing baseball or basketball versus sleeping?
Yeah, and it's a sensor, right? So the one thing we can do is, so this is where the whole firmware and software come into play, right? So on the software side, I need to show a GUI to the clinician, and the clinician can say, my patient is, it's a pretty fairly young guy, and right, they're pretty active. They play baseball, they go biking, they do other things. So I'm going to set it up in such a way that the pacemaker can account for those activities. And then within the firmware, we now say, okay, well, what do we need? We need inputs coming in, and using those inputs, we can tell what's happening. So the inputs end up being, we'll look at something called, we have something called an accelerometer. So an accelerometer, it's also in your watch, your iPhone and everything. iPhone also in your iWatch too as well. But if an accelerometer just indicates, it gets a sense of how fast you're moving, your movement, what's going on at the time. So using that sensor, we can use that to regulate, right, the heartbeats or the rate at which we send pulses to the heart. So
got it.
Yeah,
that makes sense.
yeah.
Okay.
So it's all sensors. It's one where we're picking up using the accelerometer to pick up things. We have leads that go into the heart from the device, from the pacemaker, and sometimes now we have more recent ones that don't require leads, and leads are just more wires that go directly into the heart. So the other piece now that you have taken is the heart signals. You know when the heart's beating, you know when the atrium beats, you know when the ventricle beats. You kind of, based on that, you use that to regulate and decide when am I going to need to put a pulse into the heart. So that's a pacemaker. I don't know if you have more questions on it, but
I have one more.
Okay.
I thought of one more. This is getting
Okay.
into the minutia here. But what would happen, and maybe this is why you see signs sometimes saying, like, don't do this thing if you have a pacemaker. But let's say that you were a patient on a roller coaster and you're using the accelerometer as an input.
Yes.
Can that be dangerous?
That's very dangerous. Yes, that does happen. So that's why you have that. And even lawnmowers. If you're using a lawnmower, it vibrates.
Yeah.
And so it could signal to the pacemaker that, hey, it looks like you have this person's been active. Something's going on.
Right.
So those are the things. And we have, there's standards in there already that we have to meet. And as part of those standards, we have to filter out a lot of noise, environmental noise, right? And make sure we're focused on the right stuff. So we try to do that. Sometimes some things sneak in, but we're pretty good now at being able to use a filter. And that's also where the firmware comes in, and the hardware is we can filter out a lot of the noise that's out there and focus on what we really care about. So
it's fascinating. And this is an implantable, so it's got to be pretty small. Approximately what size are these?
Mm-hmm. So I think if you can think of, we're now making ones that are really as small as a quarter.
Really?
So, right. So there's some that now as small as a quarter, and that actually goes directly into your heart. So that's the latest technology we've created. Others, honestly, pacemakers started out from being really big. They really just essentially sat on the outside of your hip. And then patients carried it around, and then now it's evolved to the point where it's really as small as really you can't even tell that it's in you, right? It's a small little device, almost the size of like the smallest is the quarter, but you have some that are a little bit bigger than that. The devices that have the leads, they use the wires. They're still a little bit bigger, but really, really small.
That's amazing.
Yeah.
And how are they powered? Do they have their own power source, or is it powered externally?
Yeah, great. You're asking great questions. Yeah. So
my engineer brain going.
Yeah. So great question. It's internally powered. That's always another challenge that we've had in the industry. So we use lithium iodine batteries, and those we put them in there, and they can last close to 10 years. Right. So in a lot of cases,
amazing.
They're pretty small, and we're always trying to reduce the size on those. So it's always good advancements there of late. So
that's incredible. So the power draw is almost zero on these things.
Yeah. Again, that's all the firmware design, because you have to make sure that it's very, very little current drain coming through.
Yeah.
So yeah. I didn't answer your defibrillators question.
Oh.
So,
go for it, please.
Okay. So defibrillators really are a kind of, they're a little different from pacemakers. They're where if your heart's beating really fast, then we have to slow it down. So that's a little different. So what we do there is your heart's beating really fast. So we send a shock pulse to the heart, and we slow down the heart then in that case. So a lot of patients, you can have patients who have what they call an arrhythmia, ventricular arrhythmia, tachycardia, anything. And so what we do in that case, the defibrillators, their job is really to make sure. Think of the external defibrillators, right? Mm-hmm. Everyone says clear shock.
Yeah, right.
Boom. Yep. And so that's what we do with implantable devices, with our implantable defibrillators. It's not an external one. It's implantable. It's in your heart. And what it does is if it detects that your heartbeat's going way too fast and you have an arrhythmia, it shocks the heart, so it takes the arrhythmia away. So
I see. Okay, so I've just learned something else here. My journey towards sparkiness. I just assumed that they would be like the external defibrillators, where they're more intended to like restart your heart, right? If your heart stops, they're going to kick it back in. But this is for when a heartbeat is too fast, it slows it down.
Yes. When it's too fast, it's you have it, and it's quibbling a lot, not at a rhythm in any way. It's abnormal for sure. So it shocks it back to normal.
Interesting. Okay. All right. Well, pacemakers and defibrillators they're life-saving devices. So I'm assuming that they're classified as class 3 medical devices. How does software development for a class 3 medical device differ from software development for, say, a consumer electronic?
Yeah, in that case, it's a lot of regulation. It's really purely the regulations there are tough to get past, and you have to really prove efficacy. You have to prove that like your devices work, or your system works and does what it's intended to do, and it does it in a safe manner. So there's a lot of emphasis on the risk to patients. So we have to make sure that we've burnt down every risk, or we've reduced risks to as low as possible in our designs. And then we also do a lot of, I think we go through, you can have multiple things. You can have like a 510K for submissions through the FDA, or you go through a full-on submission. And so the regulation is a lot more strict from the regular consumers, and we're all required. We have different standards we're required to meet and be compliant to, so that plays a role in it. So I think we've had scenarios, and it became this way just years ago, many years ago. We had scenarios where we did software and just put it out there, and the software caused problems in the field for patients, and that led to patient deaths. And so from then on, pretty much regulators across the world across the globe have been regulating the medical device software for a while now. So, yeah.
This is a complete tangent here. I just heard on a podcast somewhere, or maybe I read it very recently. I can't remember now, but it was talking about the FDA and the role that they played in regulating medical devices and pharma and things like that. And apparently back, I think it was 1920, maybe right around that time. Pharmaceutical manufacturers were not required to verify the safety of their products. All they had to do was put the ingredients, basically the cocktail of different chemicals on the label. And that's all they had to do. And there's a case study they talked about where there's some cough syrup for children that had just been invented. And there was, it wasn't cyanide, but it was something like that, that was like clearly toxic to humans that they had put in there, and they listed it on their label. So, the FDA was like, okay, that's fine. As long as you list it, that's all we check for.
As long as the warning is there.
Yeah. But a bunch of children died from it. And that was kind of the turning point at which the FDA said, okay, we're going to require more than just putting a label on to tell consumers what's in the product. Now we're actually going to require the organizations to verify that these things are safe as well.
Yeah.
Anyway,
it's very similar to ours. We have to be very careful about what we put on our labels, and we cannot encourage anyone to use it outside of the label, right? So we have to be intended use. So it's very strict, and if someone uses it outside of the label, it has to be we have to notify the bodies, regulatory bodies on that too. So in some fashion, at least capture and document it. So
okay, all right. During the course of your career, at least to date, you've progressed from being a senior engineer to a principal engineer. And I'm wondering, can you share what is the difference in terms of day-to-day responsibilities between a senior and principal level engineer?
Yeah, and it's probably even broader than that. You could say you're the new entry engineer, and then as you rise up to a principal engineer, what's the difference there? And some of it is just years of experience, getting older, losing hair, but but a lot of it too just becomes like growing responsibilities. So as an entry level engineer, you're more so really right, just doing your tasks, taking the work for the team, and taking your figuring out what your task is, working on it, and having some type of contribution. And then as you progress, you're taking on more responsibilities, where at a principal level, essentially you're leading teams. You're a technical lead on a team. You're interfacing with key players outside of your own team, right? So you end up being the face of the team, and people look to you. And then also you have more of a technical authority in a sense, right? So people expect that you know what you're doing, and you can be counted on. So that's primarily, in a nutshell, it's the difference. The way we look at it in general is we talk about your span of influence, right? So and then we talk about level of the level of independence you have, right? So principal level engineers are generally more independent than a new entry engineer. And then we talk about leadership capabilities, and also how you deliver on results. So
wonderful. Okay. What are some tips for how software teams and hardware teams can communicate effectively with one another? Maybe if you can think of any, what are some of the problems that you've seen in the interactions between these groups in the past?
Yeah, it's interesting. Like there can be a lot of different problems, but I feel if there's, in some ways, I was just talking about this too with someone. It's you can have two two flavors of this. In software, a lot of software teams are now, trying to use the Agile methodology for software development. Then you have hardware teams that, in most cases, follow a waterfall type approach. And both of those, unless you use good communication and good understanding, you could bump heads into those styles, right? So if you're not talking about it well enough. But I think the one piece for software and hardware that I found is it's the communication, right? There needs to be good communication, and we find ways to make sure that it's clear and that interface is clear. And so we try to do a better job of documenting and capturing understanding of what's the interface between hardware and software. And so as part of our designs, we write that down so that everybody knows this is it. If my hardware component is going to talk to software, this is how it talks to software. And so everyone agrees to that. And then we follow those same principles across the board so that there are no mistakes, right? So that's one way to do it. The other piece, like I said, it's really documentation is one thing, but having just the teams together and working together and just having conversations, that really helps you a ton. And it's also a way for us to ensure that we are growing, right? We're growing knowledge and sharing knowledge across both software and hardware, and building that good understanding. So yeah, that's what I'd say.
How about measuring progress with software development? With hardware, I feel like it's fairly straightforward. You can look at something, hold it in your hands, it's tangible, you can touch it, you can move it around, and you can say, yeah, I know it is supposed to be at the end, and here's what it is right now. With software, it's I don't know, for me, it seems less tangible. How do you measure progress with software development?
Yeah, it's a good one. Yeah, I'm actually reading a couple of book on this similar to this now. It's in software it is less tangible, but we have multiple ways of doing this. Like we look at we create user stories in a way. So user stories essentially says, hey, here's what I plan to do, right? And then I look at how over time, over a specific period of time, how many of those user stories have I completed? So I work on, and user stories could take the form of, well, I want to create something that can turn the color of Aaron's beard from gray to black, right? So something like
Wouldn't
that.
Wouldn't that be great? Yeah. Reverse the process.
And then you define what you consider done. Well, my done is I'm going to test it and I'm going to confirm that yes, it does. I can do this in different scenarios. So that would be, and we go for a sprint. So a sprint can be 2 weeks, 4 weeks. So we'd say, well, given my 2 week sprint, how am I progressing? At the end of my 2 week sprint, I can check to see if am I done or am I not done with this. And so that gives me an indication of progress for each team. And so I look at, in terms of metrics, we look at what we call burn downs. We look at velocity. How quickly is the team getting through all their user stories? How quickly are they burning down their backlog? So because the backlog essentially says you have all these user stories, so you have a lot of things to do, and you've taken some and you're using it on, you're trying to work on it for this sprint. Well, how quickly did you get through them? And then how much of it did you burn down? I use that to show metrics. And then obviously there's still the other regular traditional approaches of people for providing status reports and other things. But you can, with the tools we have in software, I can almost tell, as long as everyone's following and doing it right, I can go in easily and look and see, okay, hey, they're making progress. They're not making progress. So
the user story, that's a new term for me. Is that more or less synonymous with like a feature, basically?
Yeah. Yep.
Or is it more than that?
It's very similar to a feature. Yes.
Okay.
Yep.
Okay.
Yeah. So
Great.
you think of it that way.
All right. Well, this is a good chance for me to take a very short break and share with the listeners that teampipeline.us is where you can learn more about how we help medical device and other product engineering or manufacturing teams develop turnkey equipment, custom fixtures, and automated machines to characterize, inspect, assemble, manufacture, and perform verification testing on your devices. We're speaking with Idara Uko today. Idara is I feel like engineers, we always want to make the products that we work on perfect, and that can lead to scope creep and spending too much time on a particular product. So oftentimes the features that go into these products will be broken up into like a Gen 1 release, a Gen 2 release, and so on. How do you determine which features will be part of a Gen 1 release and which need to be saved for future generations of the project?
Yeah, good question. Yeah, it's all of these. They end up being discussions and negotiations between the product teams, the designers. Some things just generally take longer to do, right, and others do not. So, if you think about the way we end up doing this, because I once at one point early in my career, I was on a project for nearly. I think it took us almost 7 years to get that product out the door.
Wow.
And that's
Long
an
project.
eternity. So the market changes, everything changes way too quickly for you to take so long to develop a product. So we quickly stopped doing that. so we end up saying, well, let's figure out what you can put out. Yeah, you want to have some type of release every year, every 2 years, right? So you figure out what is it that customers want, right? And what's more urgent or what's not. So you figure out what's important to customers, and then you pick those features and say, all right, let's try to deliver this, right, in this time frame. And something that restricts you is there may be requirements for that region of the business or the customer where they need something at a certain time, so you have to deliver it at a certain time. So your time frame becomes limited. And then also your budget. You don't really have that much money to spend, so it's better for you to phase it in ways so you can spend the money. So that's what we do is we would essentially decide on, all right, this is going to be impactful in the marketplace. We think that it can make a difference for us, so we'll put it in a phase 1, and we know the things that might take us a lot longer. We'll look at the phase 2 for it, and so yeah, or Gen 2 it's what you called it, the Gen 2 release. So
great, yeah. Okay. Well, in your LinkedIn profile, one of the things that you share about your role is owning the responsibility to manage a team focused on ensuring that we build the right product or system for our stakeholders. Now, I'm being a little facetious here, but maybe especially for younger engineers that are listening to this, isn't it easy and obvious what the right product is? I mean, you're working on it, right? So how can you build anything but the right product?
That's a good one. I don't know if you've ever seen that. Have you ever seen that cartoon where it's that's someone says it says I need a swing, right? And then this engineer goes off and builds this really fancy swing that you go up, it like makes music or something like that. I'm not sure, but it looks very different. But at the end of the day, the customer comes back and says, well, I just needed the tire tied to my tree that's right here, and it's a little small swing. So it's very similar. You have to. That term is really like a validation term for us. We call it design validation. It's ensuring that you've built the right product for your customers. So, and you only know that because in engineering, and you know this too, is that someone can ask you for something, but you have to really kind of check and make sure you have a good understanding of what they're asking for, because you can end up building the wrong thing for them. So it's and that's what this is. So the way we do this is we're constantly going back and asking customers like, hey, you asked for this, but here's a prototype. Is this what you were thinking? And then they'll say, no, maybe this, and this. And it will go make modifications, come back, say, okay, all right, here's another prototype. Is this kind of what you were thinking? And eventually, gradually along the way, it was like, yep, this is doing exactly what I want. This is what I wanted. Then we go off and we go build it. And we come back. As long as we don't take too long to build it, we come back and we say, yep, this is good. So they can use it. So that's the idea. It's constantly checking in with your stakeholders or your customers and making sure, yep, you're meeting what you're actually doing, what they intend you to do. Because everything could look fine, but at the end of the day, it's still not the right product for your customers. So you want to be careful about that. So,
and that is such a perfect way to do it. I think it's so easy to create a requirements document and you send it back and forth and everyone says, yep, this is exactly what we want. But then you build a prototype. Like you say, you actually get something in their hands, whether it's software or hardware, and the customer starts using it. And even though everyone agreed to that product requirements document, there are always those cases where they get a prototype in their hand and oh, I didn't realize that it was going to be this way, or what we really need is, this other thing, this other feature here. So that the prototypes and the iterations of the prototypes practically speaking, that's the way to do it.
Yeah. I agree. Yeah. I agree.
All right. Well, what advice would you give companies that are just starting to develop their own internal software group? I mean, are there best practices like Scrum or Agile that we should be learning about? Any tools that are very commonly used, or just anything else that comes to mind that should be considered for companies that are establishing their first team of software engineers?
Yeah, and great. Like I think I may have mentioned this earlier, but I did move so I started off as an electrical engineer, worked in more the firmware area, and then I moved into more of a systems area. And the systems area is all about understanding what customers want and delivering that. And then I started, and I also went into quality, and then I now lead a software team, and we're constantly always asking about this, right? Like, how do we build our software teams? What's the right team structure? How do we want to set it up? And they're already really good, right? Good templates and good examples out there in the industry, in the software industry and software world already that we're trying to leverage and use. But at the end of the day, we step back and realize, well, what is it that we're trying to do? Our business, right? What are we trying to, for the customers we're trying to serve, how can we best serve them, right? And so you set up your teams and you set up your group in a way that you can do that. So for us, we're like as a medical device company, we're not just pure software. We're software that needs to work with a medical device. So there has to be good interoperability across with that and also with other instruments that we build. So it becomes very complex, right? And every time we're always mixing and trying to figure out what the right pattern is. One thing we do know that we're taking this from industry is, yes, going with an Agile Scrum approach is pretty much the best way for developing software, and it's merely because of the principles behind Agile. And if we follow it to the T, it's great because it's all about the customer. It's like you're trying to design things to make sure it's right for the customer, and so you're focused on that. And then you're doing what you can to get that out fast. So that's why you look at the 2-week sprints. So you look at other approaches, and then it gets more detailed on the mechanics of it. But just fundamentally at a pretty high level, that's really what it's about. So we found going with an Agile Scrum approach is working. Some of our teams do different things. Sometimes we don't do typical like sprint formats or the Scrum. We go Kanban depending on what we're working on or what those teams are working on. So we allow that flexibility of the teams. I think getting to the point where we've also realized that it's good to have, I mean, there are pluses and minuses to these things, but it's good to have it where teams are focused on doing their software development and you have the required roles that help in terms of reporting out, making sure that there's a backlog and understanding what the user stories need to be, the roadmap. So we have roles to handle that. So typically call that product owners. We have a Scrum Master on our teams. And so those two essentially lead the teams. And the teams just kind of, those two are really good, the teams run themselves and they're autonomous. They make decisions. They click and they move. So if you get it right, it's beautiful to watch.
Wonderful.
Yeah.
All right. Well, let's see. Before we end here, is there anything else that we haven't talked about that you think we should talk about?
Yeah, I think in general, I think if there are folks out there that are looking to do this for the first time or to set up a team, of course, I did mention this, but there are multiple ways. Like there are a lot of software houses out there, right? A lot of people go with vendors, right? And they grab vendors to do the work that they need to do. So I think the way we think about it is it something that's core to our offering? Is it something that's core to our company and what we bring to the table? If it is, then we want to build those teams in-house. If it's not something that's core to us, then we'll probably outsource it out and work with those teams. So, and those are some other things to consider for anyone. So who's building this, who's trying to set up a team for the first time. So I think it would, like with anything engineering, and you know this as well, is it's all about, you're trying, you're experimenting, you're learning, you're constantly learning along the way, and you make mistakes. It's fine. You bounce back, keep going. So yeah.
That reminds me of a book that we were discussing in our team meeting yesterday. It's a book called Culture Code, who one of our team members suggested I read. Have you read it?
I just sent that link out to my teams too.
Oh,
we should go
wonderful.
read that. So,
it's so good.
I've read it. I like it. Yeah.
It's one of the best teams on books on team building I've ever read, I think.
Yeah.
Anyway, it reminded me, you remember the part in the beginning about the sticks and the marshmallows and the tape with the kindergartners
and kids.
Yeah. Right. These kindergartners, for those out there who haven't heard it, don't take my word for it. Go out and buy it and read it because it's wonderful. There's so much there. But there was a study done where kindergartners were given like little, I don't know, wooden dowels, skewers with some tape and a marshmallow. And the rule was that the marshmallow had to end up on top. They had to build these structures, and the taller you could build it, the better you scored. And so this team of kindergartners would do this. And then the researchers went out and had teams of MBA students and attorneys and even CEOs do the same thing. And of course, you would assume that, well, the business school students and the attorneys and the CEOs, they're going to crush the kindergartners, right? And that was completely the opposite. In fact, they replicated this dozens of times, and every time the kindergartners won. On average, theirs were, I think, like 26 inches tall, and the MBA students were like 12 inches tall, and the attorneys were like 16 inches tall, and the CEOs were like 22 inches tall. But the amazing thing was, they said the professional groups would spend a lot of their energy thinking and strategizing and even kind of trying to figure out like where they stood on the social hierarchy, just trying to figure out their place within the group. And the kindergartners, they just jumped in. They just dived in, and it was messy and kind of chaotic, and people were talking over each other, but they were just trying different things right from the start. And that was the strategy that really ended up being the best one. So anyways, it reminded me of that.
Yeah. Oh, it's a good one. Yeah, I like it.
Well, Idara, how can people get in touch with you?
Yeah, I'm on yeah, you can reach me through LinkedIn. Certainly welcome to continue to network with others and share what I know and also learn from others as well. So I'm on LinkedIn. I'm also on Twitter. So you can hashtag UKOID. So you can also reach me there as well. So
Terrific.
yeah.
Terrific. All right. Well, Idara, thank you so much for spending some time with me on the show today. Really appreciate everything you've shared, and it's just been a pleasure to get to know you a little bit.
Okay. Thanks, Aaron. I much appreciate it. This was fun.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.